the verify strategy last time. Yeah. So today we apply this strategy to solve a simple problem. So let you see how do we apply the simple strategy. Okay, very simple but very effective. Another commonly used strategy in problem solving. Yeah, later in this class, we will have a few more places we need to apply this strategy. Okay. All right. First, thinking. Yeah. All right. So remember, in order to find the number of, because we need to go through all the possible M strings in a given text. Given text, we have a long string. Yeah, we assume there are total N characters. N. In order to search for all the possible substrings matching the given pattern, so we start from the leftmost position. Then every time we shift one position to the right until we reach the last M substring in the given text. Yeah. So that's straightforward. So that's the brute force method. Remember, later I give you two advanced algorithms. Those are advanced. You do not need to every time shift by one character. You can jump. Okay. So the advanced character allows you to jump multiple characters, based on your comparison with the current character. So very complicated. How do you know how fast you can jump, right? Yeah, so very complicated. Yeah, but here we do not jump. Yeah, every time just move one position to the right. Yeah. All right, the first thing we want to count the number of M substrings in a given text. We want to count it. Okay, yeah, it's a simple question, yeah, but we need to give an exact number as the answer. Okay, yeah, so let's try this question first. All right, yeah, so every time extract an M substring from the text with consecutive characters, yeah, and we use the location of the first character of this substring, M substring, location of the whole M substring. Yeah, so that's our definition. How do you define the location of your M substring? Yeah. The index of the first character, its first character. Okay, all right. Compare it with the pattern. Yeah, every time when we get an M substring, we do comparison. Character by character comparison. So, oh, just a minute. I need to change the pen color here. Yeah. Because I don't want to use the red color. Yeah, this color. All right. So look at here. How many comparisons we need to do? We need to do character by character comparison. Total M character comparisons here. Yeah. All right. Yeah. Okay. Yeah. But here, let's answer this question. Yeah. How many such M substrings can we found in the given text? Yeah. Given text, remember, N characters. Okay. N characters. And M substring, you know, M characters, right? M characters. Using these two numbers, N and M. Yeah. So you know, you just move one character to the right every time. Okay. You start from the index 0, then after one string comparison, you move to one position to the right until you reach the last M substring. Now give me your guess. Yeah. here we apply guess and verify. So what is your guess? Try to get the number as close to the answer as possible for the guess using these two numbers, n and m. So what's your guess? N and m.
N minus m?
That's the first natural guess. Yep. N minus m, right? Quite natural. Yeah, because the pattern has length m, but that tail we need to minus that tail, right? Yeah. Yeah. When we reach the end, there is long tail like that. So we need to subtract that long tail, right? Yeah. It's the natural guess. But the question is this guess accurate or not? We need to answer that, okay? Yeah, so our guess is n minus n. We need to do the second part, verify. Yeah, it could be wrong, so we need to verify it, okay? So when we do verification, yeah, here, just give you another idea. So how do we do the verification? When we do verification, we try the simplest case. That strategy we used before. And sometimes we try extremo case. Yeah. Here, think about. We know the relationship between m and n, m less than or equal to n. How about we consider an extremo case? That extremo case is m equals n. That's extreme case, right? Think about that. When m and n exactly same length, how many m substring do you have in your given text? 1, but based on this formula, your guess formula is 0. That means your guess not correct. How do you adjust it? You need to make adjustment. Plus, okay? So this example to show you how to apply this guess and verify strategy. You need to make adjustment. After you find some problem, make adjustment. You use the extremo case to help you do the adjustment. +1. Okay, yeah, all right. So for this case, yeah, the 0, we know the answer should be 1. So our final answer n minus m plus 1. This is the way we apply this strategy, okay, with the simple strategy. All right, yeah. Later, yeah. So here, let me do summary for this strategy. Yeah. Later, when we apply the strategy, all right. This guess step, very important. Because if you make a very bad guess, so if your guess result is far away from the answer, then when you make your adjustment, it's very hard. So you want to make your guess as close to the answer as possible, okay? Then you only need to make small adjustment, okay? But if the difference is big, you need to make bigger adjustment. That will be harder. Yeah. But the question, how to make a good guess, right? Yeah, we want to make a good guess. So not a far away, that bad guess. Yeah. To make a good guess, you need to do some investigation. You need to do some work, analysis work. Okay. You need to discover some property. Okay. After you get some partial information, property, based on that, you make your guess. That would be much better. Okay? You need to do some analysis. Yeah. So I will show you this analysis thing in our later example. Later example, I will show you. So we study some special cases. After that, when we have some partial result, then we can make reasonable guess. Okay, yeah, so we will get there quickly. All right, so next, now, when we run this algorithm, that would be simple. Okay, yeah. So here I use this diagram. Yeah, we use a for loop. Yeah, so we take the first m substring, then our for loop goes through, all m minus m plus 1 m substrings. Yeah, in a for loop, natural, in a natural way. Okay, yeah. All right, but here, let me use this as example for another method practice, another chance method practice. Okay, let me ask you a question first. Now, because the first position, the position of the first m substrate is easy, right? Yeah. 0, index 0 is the first position of our, is the position of our first m substrate. Now I ask you a question. What is the position of our last m substrate? Last, not first. First easy, trivial, but last, look at this m question, t question mark. T question mark. This gives us the first character of the location of the first character of the last m substrate. Okay, but because I do not know what is the number of the subscript, I couldn't figure out. I need to do some calculation to get this number for this question mark, right? Yeah. So can we use some simple way to calculate what is this number subscript corresponding to this question mark subscript? Yeah. Think about it. It's a simple question. Yeah. Think about it. Yeah. So first m substring. Yeah. Now the last m substrate. That's because if we know the last one, then we know how to write our for loop, right? Otherwise, how do you write your for loop? Right? So we want to know this number to write our for loop. Okay? Yeah. So any effective way you can think of at this point to calculate the subscript. Yeah. There is a Dakota.
Just subtract
Yeah, right. Yeah, you can do that way, but subtract what number? You need to be a little careful. Yeah, right? There is one possible difference. You need to really make that number right. Yeah. That's the hard part. Hard part. One difference. You may get one difference. Now we want to fix that possible one difference. Okay, all right. So here, let me remind you, we learned in our chessboard puzzle question, what method we learned in that chessboard puzzle question.
which chessboard?
That domino covering chessboard, that domino one. Invariant, that's correct. Here, can we find some invariant to help us figure out this question mark invariant number? What's the invariant number? Think about, actually our current M string, we move, it's a moving M string, right? When we move the M string, can you find something that is fixed all the time when you move M substrate. One quantity is always fixed when you move the M substrate from left to right. There is some number always fixed. What's that? The length of the M string. How about that? The length of that length never changes, right? Yeah, when you move, same length, never changes. That length is the M invariant. That length is the invariant. Okay, all right. How do you represent that length? The length, or you can, yeah, actually, although the length, you can use another way. You can consider the difference of the two subscripts. How about that? The difference of two subscripts of the two end characters in that M subscript. That's also fixed, right? That difference is fixed. So we can choose that difference as the invariant. How about that? Okay, yeah. All right. So for the first M string, what is the difference of the? Yeah. So here you can see, right? Yeah, invariant idea. Difference of two end subscripts of each subscript. It never changes. This difference never changes when you move. Okay, yeah. So let's use this invariant to keep track of the position for the last M substrate. Okay, so we set up an equation based on this difference, left-hand side for the first M substrate. So what's that? N minus 1 minus 0. So N minus 1 is the difference. Okay, yeah. For the last one, the subscript of the right end subscript N minus 1, but we use X to represent the question mark, the left subscript. This difference, N minus 1 minus X. Yeah. Then we set up this equation and solve for X. How about that? Solve for X. How about that? Okay, yeah. So the answer of X, N minus N. That's the answer. Okay, yeah, yeah. So here we get to practice our invariant method. So you can see, yeah. Especially when you need to find some accurate number. You know, you do some difference. But when you do the difference, if you do not use this way, you may get not exact number. Your number could be one away from the correct answer. Here, using this one, we can guarantee our answer is correct. Okay, yeah. All right, so here, this is the third time we use the invariant method. Remember, the second time, when we look at the size of the square, yeah, also chessboard question, but we consider size. Not chessboard, sorry. Our fake coin problem. Remember fake coin problem? Yeah. Number of wings and the number of coins. Yeah. That relationship, we use the invariant method. So for the chessboard, domino coverage, the difference of black squares and the white square, our second time using this invariant method. This is third time. Third time, invariant method. See, yeah. Very useful, very useful. Yeah. All right, yeah. So we find the last subscript index I equals M minus N. Now, when you write the for loop, it's easy, right? From 0 through that N minus N. Yeah. Now it's easy. Okay. Yeah. So you need this number, the range for the indices. Yeah. So you have the range for the indices. All right. All right. Then the last thing, yeah, the efficiency. How many comparisons? Yeah. How many, let's say, how many character comparisons? Each, because we need to compare character by character. So let us count the number of character comparisons. Yeah. For the best case, yeah, only M. Yeah. Because when you take the first M substring, you match it, you match the pattern, you get a match for the given pattern, so you're done, right? Yeah. So here we only find the first occurrence, okay? Yeah. If we need to find all the possible occurrence, then you need to still looking for the second occurrence and so on. Yeah. All right. Yeah. So here, for the best case, we just look at the first occurrence. Yeah. Worst case efficiency, you need to compare all the M substrings. Yeah. So try all the possible comparisons. So each one, you need M character comparisons, but you have this many M substrings. So you do multiplication. Yeah. So this, so you get a worst case like this. Okay. Yeah. All right. How about average case efficiency? Okay. Yeah. Average case efficiency. Yeah. Actually, this one, it's easy for the average case efficiency. Because when you move your M substring one position to the right, you know, the change every time you increase the position number by 1. So that property is a linear property. Yeah. And the distribution quite even. Yeah. So in that case, you can take the average of best case and worst case. Yeah. So this kind of average not always correct. You need to see. So if the, the case distribution linear and in a evenly distributed linear situation, you need to be careful here. Okay. Only in that case, yeah, here, every time we just increase the position number by 1, yeah. Yeah. So always that follow that rule. Yeah. So you can see, so we can use this way. Okay. Although you can use the, definition way. Yeah. Definition way. So adding up the number of comparisons for all those character comparisons for M substrings, then do the division. Yeah, you should get the same number. You should get the same number. Yeah. Yeah. All right. Yeah. So at this point, we finished this topic. Yeah. String matching problem, brute force method. This topic. Yeah. So you can see the solution is so simple, so easy. Yeah. But here we learn and practice 2 strategies or method. Yeah. Guess and verify 1. Another, we practice that invariant method. Yeah. As simple example, yeah. So give us chance to learn these 2 methods better. Yeah. Question.
Yeah, I think I missed something. Why is there a +2 average case?
M times 1. Can we understand as, because each one has this M multiple, right? Yeah. So, but the coefficient for that M is 1. The coefficient for the last one is this number. So your plus divided by 2. 1 plus this last one divided by 2. Okay, yeah. And if another way, yeah, yeah. All right. So let me, yeah, since you asked me this question, let me write a little more detail. Yeah. If some of you like to use the original definition of the average, the best case, m times 1 times m comparisons, right? The next one, you need to do 2 times m comparison, right? 2 times m comparison, all right? And the next one, 3 times m comparison, right? And so on, all the way, the last one, n minus m plus 1 times m comparison, okay? All right, then we apply the formula, the sum of consecutive integers, right? Yeah, so we know the number 1/2 1 plus m minus m plus 1 times the total number n minus m plus 1. Remember, times that n, all right? But that's the total. We need to do division by this number. So when you do division, this one cancel out. So you have this plus 2 left. M minus m plus 2 left. Okay, yeah. So if you want to work from the definition, you can do it in this way. Yeah. Still, that plus 2. Okay, yeah. All right. So we finish string matching problem. Okay, all right. Yeah. Then, before we finish this module, I'd like to give you a few more examples for asymptotic notations. Yeah, because remember, in this weekend, I will assign you homework assignment number 1. In this assignment, I need to give you a few questions, relatively hard, but we need to use these examples. Okay, yeah. So you need a background of these examples, okay, for those questions. So let me start question 2.5. Okay, yeah. All right, show that n to the dth power belongs to little o of exponential function a to the nth power. Yeah. Here, in order to make this question relatively simpler, I make assumption d greater or equal to 1, and then let us assume d as integer first. Later, we will remove this assumption. Yeah. First, let us consider d as integer first. Yeah. And then later, we can remove this assumption, integer assumption. Okay, all right. Yeah. So here you can see this function, n to the dth, it's a power function. It is a power function. The variable n is the variable. It's a discrete variable, but variable at the base. The exponent is constant, so it's a power function. But this a to the n, it's exponential function. Variable at the exponent. The base is a constant, a greater than 1. Yeah. So these two different functions. Yeah. And here, we want to use the L'Hopital's rule. L'Hopital's rule. Calculate derivatives. L'Hopital's rule. Okay, yeah. All right. So here, we assume d could be any integer, any positive integer. But later we will remove this assumption. Okay, yeah. This in my proof here, let's say for the simpler version, we make this assumption, integer assumption. Okay, yeah. All right. Now, let me show the work. How to apply L'Hopital's rule. Because for little o, we need to calculate the limit, the ratio of two functions. Yeah. Yeah. But when we apply the L'Hopital's rule, remember, we need to change the discrete variable to continuous variable first. So here, let's write a continuous version of these two functions directly. Okay? So we can take derivatives. X, we use X to replace discrete variable M. So we can take derivatives. Yeah. All right. But when we take derivatives, we need to check the indeterminate form, right? So no problem, because this is a infinity over infinity indeterminate form. So we can apply the L'Hopital's rule. Okay, yeah. Then the formula, the numerator derivative for the power function. Yeah. Formula d times x to the d minus 1 power. That's the formula for the power function. Okay, yeah. Derivative of the denominator, another formula, natural log of a times the original exponential function, a to the x. Yeah. All right. So that's the first time we apply the L'Hopital's rule. After it, can we get the answer still? Not yet. Still, we cannot see easily the answer. Yeah. But it is still another infinity over infinity indeterminate form, right? Yeah. That means we can apply L'Hopital's rule another time. Second time. Take derivative the second time. Numerator and denominator. Yeah. The second time, d minus 1 this time. And the d x to the d minus 2 power. D minus 2 power. Okay. And denominator natural log of a squared times a to the x. Okay. All right. Still, if d minus 2 is a positive integer, we need to apply L'Hopital's rule another time, and so on. Keep applying L'Hopital's rule until it's not an indeterminate form. If it is an indeterminate form, we always need to apply L'Hopital's rule here. See? Yeah. So let's assume we apply L'Hopital's rule all the way to the last one. Okay. Which one is the last one? Okay. Yeah. First, d factorial. And when you look at the variable part, x to the d minus d. D minus d is 0, right? D minus d is 0. X to the 0, that's 1. 1 is not a variable, it's a constant. When the numerator becomes a constant, it's not an indeterminate form. That means we should stop. So we get to the point we need to stop. We can stop at this point. Okay, yeah. And denominator, because we apply the L'Hopital's rule d times. So natural log of a to the dth power. All right, yeah. So then let's simplify this expression. Numerator is a constant, d factorial constant. Denominator, natural log of a to the dth power times exponential function a to the x. It's another indeterminate form, and we can see the limit immediately because the denominator goes to infinity. A numerator is a constant. Denominator goes to the infinity. Okay. So the answer is 0. The answer is 0. Okay. Yeah. So for this continuous variable version, the ratio of the two functions, its limit is 0. So we can go back to the discrete variable version and to the infinity and to the d's over. Oh, this time we need to use n. Okay, also 0. Okay, yeah. So it's legal. We can move from this continuous variable version limit to the discrete variable version limit. The reason I explained last time, because how do we approach to infinity? How do we make our x variable approach to infinity? Anyway, right? Yeah. The way to go to infinity anyway should be correct here when we look at the limit. Anyway to the limit. Here we just take the consecutive integer way. Okay, consecutive integer way. That's legal. So we can get this discrete variable version. So that gives us this little o asymptotic notation. Little o. Okay, yeah. All right. Now we complete the proof for this one. Yeah. After we complete the proof of this one, yeah, we can modify. So this d is not necessary integer. It could be any positive real number. Positive real number. Because if it's not integer, we can find it must be between two adjacent integers, right? You can find it must be between two adjacent integers. Yeah. Then can you get it? Then you only need to do some small adjustment, then you can get it. After you know it is between two adjacent integers, then you apply the result of this question, you can get your answer quickly. Okay? Yeah. Think about it. Yeah. Not that hard. Not that hard. Okay? Yeah. Not that hard. Yeah. So if you like me to say a few more words, yeah, I just use 2 minutes. I can show you how to get that. Okay. Yeah. All right. Yeah. So if d not integer, okay, d is not integer. Yeah. If d is not an integer, yeah, then we can find an integer k such that k less than d less than k plus 1. How about that? Okay, it must be between two adjacent integers. Okay, it must be between two adjacent integers. Okay, all right. Now we use these two results, we can get the answer. Okay, so one result, n to the k plus 1 is in big O of a to the n. That's just our integer version of this question, k plus 1. Okay, all right. Second result, can you see n to the d belongs to big O of n k plus 1? Can you see that? Okay, can you see that? Right? Yeah. To see that, it's very easy. when we write the limit n to the d over n to the k plus 1, you do cancellation. The numerator is 1, denominator is k plus 1 minus d. We know this is a positive number, right? Positive constant. And to some positive constant, so the denominator should goes to infinity. Numerator is 1, denominator to infinity, so the limit is 0. If the limit is 0, we get this little o. Okay, can you combine these two to get this n to the d in big O of a to the n? Yeah, combine these two results. Yeah, right. Yeah, so you can get that. Yeah, right. Yeah, so n to the d, when you comparison with n to the k plus 1 already in big O, and n to the k minus 1 comparing with the exponential function, another big O, little o, yeah. So there you compare with the larger a to the n, even smaller, right? Yes. So yeah, because actually you do this. N to the d, if you compare with the exponential function directly, this time you do this. The product of the limits, okay? N to the d over n to the k plus 1 first. And the second limit, n to the k plus 1 over a to the n. How about that? The product of these two limits. And we know both limits 0. 0 times 0 equals 0, right? So we prove it. By calculating this limit, we prove it. Okay, so when d is not an integer, so we can use our integer result, we prove it. Okay, but this time we do not need to apply L'Hopital's rule. Yeah. Although we can, if you like, we can apply L'Hopital's rule, but we won't have factorial, right? Because that d not integer, how do you define factorial when d is not integer, right? You won't have that factorial thing. Okay, so that's why we try to avoid L'Hopital's rule, because we don't know where to stop, right? Yeah. There is no factorial, so we don't know when do we stop, right? Yeah. How to stop? Okay. Yeah. All right. Yeah. Yeah. Okay. So now we finish this question completely. Okay. We finish this question completely. Yeah. All right. Yeah. Yeah. All right. But this right half blank space, I need to give you more examples. I need to erase. All right. Yeah. So in my video, I recorded. Yeah. But here, because I needed the space here, I have to erase this part. Okay. Yeah. So if you couldn't, catch up with the notes taking, so you can go back to the video. Okay. All right. So I need to erase it, this part. Yeah. All right. All right. There. Here, still this question. Yeah, because we just finished the proof of this question. Then I want to give you some useful information for a homework question. Yes, I haven't posed, yeah, but this information is useful for one homework question. Okay, yeah, I make some comments. Yeah, these comments will be useful to answer your homework question. Okay, all right, so let me look at, yeah, so here, let's just look at this. This is the result. Now, since we prove it, so we can apply this result when we need it. Okay, yeah. So now this D could be any constant, right? Yeah. After the proof, this D could be any constant. How about, think about, your D is a constant this big. How about that? Here, I put 1 million. So it's a big constant, okay? Big constant, all right? That means I can write this power function as n to the 1 millionth power. Do you feel this expression is a very large one? Huge one? Really? So in your mind, in your intuition, yeah, because in your impression, it's a huge, big, huge expression, right? Okay, all right. So sometimes your intuition may not be reliable. Your intuition could be wrong. Okay, yeah. Here, I try to generate some false impression for you. Yeah. Here, in a homework question, yeah, try to create some false impression to distort your intuition. Okay, to make distortion for your intuition. Yeah. All right. So this is one expression. Then another one, exponential function. We only need a greater than 1, right? If it's greater than 1, we have this result, right? No problem, right? Now, I take a greater than 1, but I take it this way. 1.000 many 0, 1. How about that? So many 0, then 1. Based on your intuition, this is a number so close to 1, right? Then raised to nth power. Okay. Now I ask you to compare these two functions. Which one grows faster? Think about that. If you use your intuition, you need to be careful. If you use intuition, you really need to be careful, right? The first one looks huge. The second one very close to, the base close to 1, right? So close to 1. Although raised to nth power, well, yeah, but if you replace to 1, that's 1. If you just ignore the little tiny difference, 0, 0, so many 0, 1, if you ignore that, it becomes 1. 1 to the n, also 1. So think about that. Yeah. All right. But you need to trust this formula. This formula must be correct. We prove it. You need to trust this result. Okay? Yes. Okay? Yeah. That's a homework question. Yeah. So think about that. Okay? Yeah. All right. When you see that, you need to really connect to this background, this example. If you just answer based on intuition, very likely you get a wrong answer. Okay, all right. All right, so let's move to next question. This time, log base 2 of n belongs to little o of root of n, square root of n. Square root of n. Okay, yeah, all right. So this time, let's apply L'Hopital's rule another time. Yeah, L'Hopital's rule. Okay, yeah, all right. Let us write the continuous version for x, continuous variable version. Okay, so we can take derivative, numerator, denominator. Numerator, log base 2. Yeah, so we can find that formula. The formula is, The formula is a little wrong. Yeah. Okay. Yeah. The formula, there is a constant here. Okay. The formula, when you take derivative, there is a natural log of 2 constant in front of this log base 2 of x. Yeah. There is a natural log of 2 constant. Yeah. So here I missed that part. Natural log of 2, we know it's a positive number. Okay. It's greater than 0, but it's a constant. It's a constant. Okay, positive constant. Okay, then multiply that log base 2 of x. Oh, no, sorry. Sorry. Yeah. Here we haven't applied the derivatives. Yeah. Here I only change denominator root of x to its exponent. I write it as 1/2. I only made that change. I haven't taken the derivatives. Yeah. So next step, I take the derivative. So you will see that natural log. Okay. Yeah. 1 over natural log of 2 times x. Yeah. Bracket. Reciprocal. But that reciprocal, you need to multiply that natural log of 2 constant. That constant is a positive constant. Okay. Then the power function you can apply to x to the 1/2 power. You can also apply, you get this expression, power rule. After simplification, you get this expression after simplification. Now it's not indeterminate form. It's not indeterminate form. The denominator goes to infinity. Numerator constant, so the whole limit must be 0. When the whole limit 0, so then you can go back to the integer limit version, that is limit n goes to infinity log base 2 of n over n. This limit must be, root of n. Yeah. This limit must be 0. So you get this little o asymptotic notation. Okay, yeah. So this is the next example related to the log function. So here, the second example, we compare log function with power function. The first example, we compare power function with exponential function. Yeah. Okay, so we know which one grows faster eventually. Yeah. The second one, when we compare log function with power function, which one grows faster eventually, we have a result. Yeah. All right. Yeah. Then another example, let me erase here. Another example, also important for a homework question. Yeah. So I need to talk about this one. Yeah. This time, natural log of n. Yeah. We change the log base. Yeah. Actually, it's not a big change. Still log function, just base. Here we use natural log base e. Base e. Yeah. I hope you know that e constant, right? Natural log base e constant. Something like infinite many digits. Yeah. So it is an irrational number. E. Okay. Yeah, that's e. Yeah. This e, actually in calculus, how to get that e? N goes to infinity. 1 plus 1 over n to nth power. This limit is e. That limit is e. Okay, so the e number is this one. Okay, just the background. Yeah. All right. So natural log of n belongs to little of n to the dth power. And what is this d? Here, I need to give you what is this D? All right, yeah. So here, this D, I have to erase. This D is greater than 0. Here, I do not say integer. This D, if it is a positive number greater than 0, then this result is correct. This result is correct. Yeah. All right. So let me show this result first. L'Hopital's rule, here we can still use L'Hopital's rule. Yeah. All right. And we write a continuous version, natural log of x over x to the d power. Okay, because it is infinity over infinity indeterminate form. So we can apply the L'Hopital's rule. Okay, yeah. Now let's take derivative of the numerator 1 over x. 1 over x. Denominator derivative, apply the power rule, d times x to the d minus 1 power. Yeah. Two formulas. Yeah. After that, then we need to simplify. After simplification, we get this expression. So it is not a determinate form. 1 over d times x to the d power. See? Yeah. Yeah. So 1 constant, this d constant, but x to the d, this part. Remember this d positive. X to the d power, d is a positive number. And when x goes to infinity, x to the d power also goes to infinity. Yeah. Denominator goes to infinity, the numerator constant, so the answer is 0. If the answer is 0, then we have that little note. Yeah. Here I do not write that discrete variable version of the limit. So yeah, we have that, yeah, but we make our conclusion. Natural log of n belongs to big O of n to the d. This d we only need it's a positive number. That's enough. If d is a positive number, we have this result. Okay, all right. So now another homework question. Similar to our first one, I make a comment for another homework question. Yeah, because here the requirement is d greater than 0. That's enough. We have this result. Now, how about this time I selected d equal 0.000, many zeros at 1. Okay, very small, but it's positive. No problem, it's positive. Okay, now I ask you to compare one natural log of n and another one, n to the 0.000001. Which one grows faster eventually? Yeah. Right? If you use the intuition, you need to be careful. And we have our result here, right? Your intuition one side, another side, our result. Okay, these two homework questions. You need to be very careful. These two. Okay. Yeah. All right. Yeah. So we finish this module completely. Yeah. But our first half of this lecture near the end. Yeah. So when you come back at 7 o'clock, we will start our module 3, new topic, module 3.